All right, let's solve the question above. The question says a flint beam is made up of two timber joists, 10 centimeter wide and 24 centimeter deep. Hold on, let's explain that part. All right, we have two timber joists, which is 10 centimeter wide, right? So if you look at this line here, from this point to this point, like this side is one timber, and this other side is another timber. And you can, if you look at that dimension, 10 centimeter, 10 centimeter, and the depth of the two timber is 24 centimeter. All right, so let's move on. And 24 centimeter depth with 2 centimeter thick steel plate, 16 centimeter, placed symmetrically between them, firmly attached to both. The meaning of that is we have a steel that the dimension that has two, the dimension is 2 centimeter, which is that is 2 centimeter thick, and the depth is 16 centimeter. This steel is placed symmetrically, in inside the two timber. I hope you understand. You can see part of the steel is at this side and part of the steel is at this side. I hope we understand. All right, so and I said the plate is recessed into groove cut in the inner face of the built up section, maybe taken as 20 centimeter by 24 centimeter. The meaning of that is this. Of course, when you place this steel plate inside the timbers, the dimension remain the same. You understand? So by the time you combine them to when they are separate, you know, if this timber is standing alone, this timber is standing alone, the dimension will just be 10 centimeter 24. This one too will be 10 centimeter 24. But immediately you combine the two together and you attach this steel between them, then the dimension will now become, from this point to this point will now become 20, and from this point to this point will now become 24 centimeter. I hope you understand that. So that is what the question is saying. So they say we should calculate the moment of resistance. Of the combined section when the maximum bending stress in the timber is 7.5 meganewton per meter square. What is then the maximum stress in the steel? Take the modulus of the steel to be equals to 20 multiplied by the modulus of the wood. All right. So having understood this, you also need to understand the diagram, and you are always going to be drawing the diagram from the what? From the question. Exactly. All right. So now I have explained this diagram. So now this one is the stress distribution diagram of this whole section, and why this one is the stress distribution diagram of the steel section only. I hope you understand. All right. So inside this section, we are having two things inside. We have our wooden section, the stress distribution for the wood, and we also have for the what? For the steel section there. Do you understand? So it comprises of the whole section. I hope you understand. All right. So now, for us to solve this question, the first thing we are going to understand is the question already told us that the maximum bending stress in the timber is 7.5 meganewton per meter square. And where do we have the maximum stress in the timber? When they say timber is also wood, exactly. So it is at 12 centimeter from the neutral axis. Do you understand? So it means that the maximum stress for our wood, the maximum stress for the wood is going to be what? 7.5 meganewton per meter square, and this is at 12 centimeter from what? From the neutral axis. Exactly. All right. Now again, we are also going to have another stress in the wood again, and this stress at this time is going to be at 8 centimeter from the neutral axis. So we are going to get the maximum stress here. You can see between here and here. So, and how do we get that? So let's just denote that with another. So let's take bar here. So this stress that we want to calculate is at 8 centimeter from the neutral axis, and it is at this point. So this is going to be equals to the maximum stress in the wood at 12 centimeter from the neutral axis multiplied by our distance, that is from this point to this point, which is 8 centimeter, which we can say y1, then over y2, and then the distance from the neutral axis to the top here is going to be what? 12. So if we substitute, we are going to have 7.5 multiplied by 8, then divided by what? Divided by 12. So by the time you press that in your calculator, you are going to have the value is going to be 5 meganewton per meter square at 8 centimeter from the neutral axis. So if you press this in your calculator, this is what you are going to have. So the next thing we are going to be calculating is the maximum stress in the steel at 8 centimeter from the neutral axis. You can see this is the stress distribution diagram for the steel, and from this point to this point is 8 centimeter. So we are going to find the maximum stress here. So we are going to denote that with this. So now what will be the formula that we are going to use here? You are going to recall that we have a relationship for stress in a steel and the stress in a wood, and we know that relationship is modular ratio multiplied by the stress in a wood. So the stress in a steel is equals to the modular ratio multiplied by what? Multiplied by stress in the wood. All right. So our modular ratio here is going to be, and don't forget that modular ratio is what? Is modulus in the steel all over the modulus in the wood, then multiplied by what? Multiplied by the stress in the wood. All right. So now this will be equals to the modulus in the steel over modulus in the wood is going to be, if you divide both sides here by the modulus in the wood, you are going to have modulus in the steel over modulus in the wood to be equals to what? 20. So here we are going to have 20 multiplied by what? 20 multiplied by the stress in the wood at 8 centimeter about from the neutral axis. It's nothing but what? 5. So here we are going to have 5. So our answer here is going to be what? 100 meganewton per meter squared. I hope we understand this. So here we are going to have here to be 5. We are going to have 5 meganewton per meter squared. So here we are going to have 100 meganewton per meter meter squared. All right, so that's it. I hope we understand that. All right, so now the next thing we are going to calculate is the total moment of resistance. The total moment of resistance of the section. Of course, the question says we should find the maximum stress in the steel. So the maximum stress in the steel is 100 meganewton per meter square. So we are done with that. So now let's go for the moment of resistance of the combined section. So the moment of resistance of the combined section, that is the total moment of resistance, is going to be equals to the moment of resistance of the wood plus the moment of resistance of the steel. Wood is wood, and this one is steel. All right. Now let's go for the moment of resistance of the wood. All right. So moment of resistance of the wood. But before we do this, let me quickly show you the formula that we are going to use. So from our Flitched equation, we know that moment is equals to stress multiplied by section modulus. So this is the formula we are going to be using. So we can therefore say moment of resistance of wood will be equals to stress in the wood multiplied by what? Multiplied by section modulus of the wood, right? But if you just write this now, you cannot just apply this formula here directly. Why? Because this thing is inside the wood. So now I'm going to clean it, then I'm going to explain properly to us now so that we grab the concept clearly. All right, now if you look at this diagram now, if you want to calculate the moment of resistance of the wood, how are we going to get this? Since this is the wood here, right? This is the wood. The wood is the whole section, the bigger rectangular section there, and this is the steel section, right? So for us to calculate the moment of resistance of the wood section, is going to be the moment of resistance of the rectangular section 20 by 24 section minus the moment of resistance of this rectangular section 2 by 16, which is yes, it's going to be 2 by 16 section. So that is going to be the moment of resistance of the wood. I hope we understand this. That is the moment of resistance of the rectangular section 20 by 24 25 24 centimeter minus the moment of resistance of this rectangle section, which is 2 by 16 centimeter. I hope we understand that. So that is going to be the moment of resistance of our wood. All right, so and then we are going to be applying this formula there. So here the first one is going to be the stress, sorry. All right, I need to write legibly. All right, so this is going to be the moment of resistance of, okay, let me just write the formula. And let's say this is this formula here is for 2 by, let's put it in bracket. So this is for the 20 by 24 section. So 20 by 24 section. All right, I think it's supposed to be in centimeter. Okay, let's write it properly well. So let's say this is 20 centimeter by 24 cm. All right, so minus the stress multiplied by z, and for the section it's going to be 2 centimeter by 16 cm. All right, but I love my work to be on a straight line. I don't like the way it is like this. Please just bear with me. Okay, what can I do? All right, so since it is big, since it is big and small, so let's use this one. Since this one is big rectangle, so this one is small rectangle. I hope you understand. I think it is perfect that way. All right, as an engineering student, you need to be creative. You need to be when you are solving a question, you need to show that you really understand what you are doing. Is that clear? All right, so now let's move on now. So now we know that this is the moment of resistance of the rectangular section, of the big rectangular section, which is 20 by what? 24 centimeter. All right, so now this will be equals to, so the moment of resistance of the wood will be equals to, now let's go with this section now. So now we need the moment, the stress. Now if you look at this section now and you trace it like this, the stress is going in alignment with what we have here, which is 7.5 mega Newton per meter square. So that will be the stress we are going to be using to analyze this rectangular part. So here we are going to have, it means the maximum stress here is going to be 7.5. So 7.5, don't forget it is mega. Mega is times 10 to the power of 6. Yes, multiplied by the section modulus of the rectangular section there. Section modulus is nothing but what? It's nothing but BD square. Yes, BD square divided by 6, right? All right, so now the base is 20, while the depth is 24. All right, but don't forget our stress unit here is in meter, and here this one is in centimeter, so we are going to divide them by 100, right? So now BD BD square over 6. B, that is the base. So that is 20. 20 divided by 100, that is 0.2. So here we are going to have 0.2 here multiplied by our depth. Our depth is 24. So it's going to be 0.24 squared. Then divided by 6, right? Then minus the stress here is for the small rectangle, that is for the small section, that is 2 by 16 section. So if you trace it like this, the stress that we have here, don't forget we are having two stress here, right? But the stress distribution diagram that we are dealing with is this first one here. Is that clear? So we are going to be using this 5 to analyze the question here. So it's going to be 5. So we are going to have 5, but it is in mega too, so it's going to be 5 multiplied by 10 to the power of 6, then multiplied, let me just put my hand here, multiplied by BD cubed divided by 6, right? So the base is 2 and the depth is 16. So if we divide 2 by 100, we are going to have 0.02 multiplied by the depth, which is 16. 16 divided by 100, that's 0.16 squared divided by 6. I hope you know how all these things come back now. The section modulus of a rectangle is BD squared divided by 6. So that is what we apply there. All right. So here, I think we can put it in bracket. We can put it in bracket. But for me to put this in bracket, I'm going to be facing some difficulties. All right. So show that they are together. Let me just do it like to show that they are together. All right. So now, the next thing you are going to do now is to press this value in your calculator directly. If you press 7.5 multiplied by 10 to the power of 6, multiplied by 0.2, multiplied by 0.24 squared divided by 6, and you might punch your answer, or you can still press directly. Exactly. So minus 5 multiplied by 10 to the power of 6 multiplied by 0.02 multiplied by 0.16 squared divided by 6. So our answer here, that is the moment of resistance of the wood, is going to give you nothing but what? It's going to give us 13,973. 13,973 point what? Point 0.4. So this one is going to be Newton meter. All right, so that is what we are going to have. All right, so the next thing we are going to do next is to calculate the moment of resistance of the steel. So moment of resistance of the steel. All right, moment of resistance of the steel now. So this is the steel. This is the diagram for the the steel section. That is the stress distribution diagram for the steel. All right, so we are still using the same formula here. Stress multiplied by the stress in the steel multiplied by the section modulus of the steel. That is what we are still using. So this will be equals to, so now the maximum stress here is 100. So don't forget it is 100 mega. So this is going to be 100 multiplied by 10 to the power of 6, then multiplied by the base. Our section modulus of the steel here, it is still a rectangle, and we are refined back to this section here, that is 2 by 16. So it is still base multiplied by depth squared divided by 6. So the base is going to be 0.02 multiplied by what? Multiplied by 16 there, that is 0.16 squared, then divided by 6, right? So you can just everything divided by 6. All right. So if you do this, if you press this directly, your answer is going to be 8,533.3. So it's going to be 8,533.3 Newton meter. So that is what you are going to have. All right. So now we can therefore substitute now for us to get the for us to calculate the combined moment of resistance now. So now if we substitute here now, we are going to have our total moment of resistance or combined moment of resistance, which is moment of resistance of the wood, which is 13,973.4 plus the moment of resistance of the steel is 8,533.3. So if you sum this together now, what are we going to have? We are going to have 22,506. 22,506 point what? 0.7. So this is going to be Newton meter. So here is the solution. Here is the solution to the above question. I hope this question is well simplified and well understood. You can let us know that in the comment section. And if today is your first time of coming across our content, please don't forget to give this video a thumbs up, and don't forget to click on the subscribe button and hit on the notification bell so that anytime we upload a content like this, you'll be the first to receive the notification that we have uploaded other content. And once you once you click on the subscribe button, you are going to see join. You can also join our membership group so that you can have access to premium content like this. And don't forget to share this content with your friends from various institutions who might be in need of this. Thank you. Please drop a nice comment for us. Thanks.